sustainable aviation fuel. Now we are going to start that session. As you know that international civil aviation organizations has set up goals to reduce greenhouse gas emissions and agreed for implementations of CORSIA by blending of SAF with ATF. As you know, India is set to onboard the CORSIA regulations mandate from 2027. Various organizations have declared that they have developed various SAF technology based on different feedstocks. So a lot of challenges are there in terms of feed variations, catalyst, process selectivity, conversions of different technologies, and ultimately that viability. So all our eminent speakers are there. 6 speakers will be there. So they will be presenting their thoughts. So first we will invite Mr. Lalit Kumar, Chief General Manager, BPCL. May I request Mr. Lalit Kumar?
Thank you, Session Chair, for setting up the tone and inviting me to deliver the first talk of this session. I'm going to talk about hydroprocessing of used cooking oil for producing sustainable aviation fuel using BPCL indigenous catalyst. You will agree with the fact that climate change is one of the most urgent challenges of our time. It requires concerted efforts and commitments globally to take corrective measures to address this grave concern. Today, not only we need operational improvements and technology advancement, but also, and more importantly, we need the fast adoption of alternative fuels and green sources of energy. Ladies and gentlemen, decade until 2030 is our window of opportunity. Actions taken now will determine the ability of our future generation to sustain on this planet. Sustainable aviation fuel is a green substitute for jet fuel or ATF with at least 80% less life cycle carbon emissions. It has a great potential to decarbonize the aviation sector, which contribute around 2% of the global carbon emissions. In sync with the need of the hour and as part of its self-reliant India initiatives, BPCL has come up its hydroprocessing catalyst which selectively and effectively convert used cooking oil and other feedstocks into sustainable aviation fuel. So this is the outline of this talk. Anyway, we are going to see them as we go through this presentation. So I will skip this. So now if you see the SAF global perspective, it is mainly governed by the CORSIA mandate. CORSIA stands for the Carbon Offsetting and Reduction Scheme for International Aviation, and which will come in force from 2027, and it will mandate use of SAF in ATF for international aviation. As per International Civil Aviation Organization goal, all states with more than 0.5% stake in international aviation has to comply to the CORSIA. These are the states which are marked in blue and the green in the picture in the middle. However, the states which are marked in yellow are exempted states, which means that international flights which are taking off and landing in these states will not come under the purview of the CORSIA. So what is the objective of the CORSIA? CORSIA aims carbon neutral growth of international aviation sector by stabilizing its CO2 emissions to 85% of 2019 level. If you follow the picture on the right hand side, though the operational improvements and aircraft technology advancement will contribute to some extent, our use of the CORSIA eligible fuel is going to be the biggest measure in the ICU basket of measure to stabilize these emissions. Now, if you look at SAF Indian perspective, international airlines and international segment of domestic airline will come under the purview of the CORSIA. And based on the recommendation of National Biofuel Coordination Committee, Ministry of Petroleum and Natural Gas India has already approved 1%, 2% and 5% blending of SAF in ATF respectively for the year 2027, 2028 and 2030. And accordingly, the oil making companies in India are advised for setting up and commissioning of their SAF plants. India, which is going to be third largest consumer of ATF in 2007 soon, will consume around 30,000 tons per day ATF in 2027, and which will go to 35,000 tons per day by 2030. Now we follow the blending target set by the Ministry of Petroleum and Natural Gas India. India will be requiring around 300 tons per day SAF in 2027 and around 1750 tons per day SAF in 2030. Now this gives the current ASTM approved technology pathways to produce SAF. Currently 11 technology pathways have been approved by ASTM to produce SAF, out of which HEFA, FT and alcohol to jet hold promise in the Indian context. ATJ involves the feedstocks like ethanol and isobutanol, which are obtained from the 1G and 2G biomasses. And these alcohols undergo series of chemical conversions to produce SAF. This technology is currently growing and maturing, and only recently the technology has got its first commercial plant at Georgia, US. FT feeds on municipal solid waste and agricultural residue, which are gasified into syngas, and further the syngas is converted into the SAF through the FT synthesis. On the other hand, HEFA, which stands for hydroprocessing of esters and fatty acids, converts the feedstock like edible, non-edible oils, and animal fats to produce SAF. Now, if we further talk about the HEFA or hydroprocessing route, it is the most mature, proven, and economical SAF technology available today. It feeds on the feedstock like tree-borne oil, animal tallow, UCO, pea fat, palm stearin, which are first pre-treated to remove the impurities like phospholipids, and then they further undergo the series of reactions like hydrogenation, hydrogenolysis, hydrodeoxynation, and the cracking to produce SAF. So technology, to date, SAF technology has powered more than 95% of the SAF flights, and the production cost for this technology is lowest. It is around 90 to 130 rupees per kg, which is lower than any other approved technology today. Now further, the opportunities for the HEFA lies in increasing demand for the jet fuel, which will in turn increase the demand for the SAF as well. It will add value to the low value waste cooking oil. Also, the SAF production cost is lowest, so it makes this route economically attractive. And it gives energy security and independence to the airlines, especially in the scenario of uncertain fossil fuel scenario. Having said that, there are few challenges also for the HEFA in the Indian context. Though the feedstock is available, feedstock aggregation and collection remains a challenge. And though the ecosystem in India is there, however, it is in the growing stage, and it still has to become mature and robust to collect the UCO from the last door availability. There are some policy interventions required also to make this feedstock available on such sustainable basis. There is a poor health awareness also for using cooking oil in India. That also needs to be worked out. And there is this HEFA will also face the industry competition from the industry like soap and oleochemical, which utilize a similar kind of the feedstocks. Now coming to BPCL indigenous catalyst for the HEFA route. BPCL has developed hydrodeoxynation and hydrodewaxing catalyst, and accordingly two-step conceptual HEFA process to produce SAF. These are the key feature of first step hydrodeoxynation catalyst. This catalyst convert UCO or triglyceride molecule into C6C18 hydrocarbons. It is a bimetallic catalyst which is supported on highly hydrothermally stable mixed oxide support. And this catalyst is capable of performing hydrogenation, hydrogenolysis, hydrodeoxynation, and cracking of the UCO. It selectively converts the UCO or triglyceride molecule into kerosene range hydrocarbons, which are suitable to make SAF. This catalyst is already patented for the green diesel, and recently in 2023 we also have filed the Indian patent for this catalyst. And this is scaled up at 100 kg scale. Now these are the key features of the second step hydrodewaxing catalyst. So this catalyst takes C10 and C18 hydrocarbon from the first step as a feedstock and isomerize these hydrocarbons into the SAF range hydrocarbons. This catalyst is again an improvised version of BPCL patented commercial catalyst, which is tweaked and attuned for the SAF application. It is basically a bifunctional zeolite catalyst comprised of metal and acid function, and it is further optimized for the acidity, surface area, and aspect ratio to selectively hydroisomerize the N paraffins into SAF range isoparaffins. The uniqueness of this catalyst is that cost is only 1/5 of the commercial catalyst, and this as well is scaled up at 100 kg scale. Now this is to give you the overview of the conceptual HEPA process. It is a two-step process. The pretreated feed is first hydrodeoxygenated in a hydrodeoxynation reactor, where the oxygen is removed to convert this feed into the paraffins. And after removal of the water and the off gases and lighters and heavier fractions, the C10, C18 paraffins are further hydroisomerized in the second step to produce sustainable aviation fuel and the byproducts like green diesel and green gases. Now this gives the performance of the first stage hydrodeoxygenation catalyst. Now if you follow the bar graphs on the left hand side, two bar graphs, they give the kerosene selectivity, UCO conversion and hydrodeoxygenation selectivity for the two catalysts, nickel, tungsten and NEMO. These catalysts are prepared using different support A and B, A, B and C, while support A and B are the single oxide support C is the mixed oxide support. So you can clearly see the mixed oxide support has resulted into the better kerosene selectivity and the UCO conversion. Now if you see on performing the time on stream study for these catalysts, if you follow the two graphs in the middle, so we found the activity of both these catalysts is highly stable as the UCO conversion and kerosene selectivity remain intact. And also if you compare the properties of the hydrodeoxygenated oil produced using these two catalysts, the properties are quite similar except the core point for the nickel tungsten is somewhat lower. To sum up, the best hydrodeoxynation catalyst has resulted into kerosene selectivity of 78%, hydrodeoxynation selectivity more than 99%, and UCO conversion 94%. Now this gives the performance of the second step hydrodewaxing catalyst. So if you see the bar chart on the left hand side, it gives the SAF yield. The SAF yield is extremely good, 92% for this step. And if you follow the pie chart, it gives the overall product distribution of the process. You can see that the major chunk of the product is SAF, which is 74%, and which is followed by the water, hydrocarbon gases, green diesel, and gasoline. If we compare the SAF properties with the ASTM D7566 specifications, which are the specifications for up to 50% blend of SAF in ATF, the SAF produced SAF comply to all these specifications except the aromatic content, but that is not a concern because ultimately this is going to be blended with the ATF. However, the noticeable thing here is the high calorific value of this SAF. The calorific value is high, which translates into the better fuel efficiency for the airlines. To conclude, as part of the Self-Reliant India initiatives and net zero goals, BPCL has developed cost-effective, scalable, excellent quality, higher yields, high activity indigenous catalyst for the SAF production through the HEPA route. Catalyst is successfully scaled up at 100 kg scale and have resulted into promising 74% SAF yield, and the produced SAF meet ASTM D7566 specifications. This is the way forward for the BPCL. We will be going for the couple of tie-ups, like tie-up with suitable technology partner for joint SAF technology demonstration, then tie-up with the feed aggregator for sustainable feed supply, further tie-up with the catalyst manufacturer for the toll manufacturing of the catalyst, and finally we will be going for setting up the SAF plant at BPCL refinery and start production of the SAF in January 2027. With this, I come to the end of my presentation. Thank you, audience, for patiently listening. And thank you, organizers, to give me this wonderful opportunity to speak in this forum. Thank you all.
Thank you.
Hello. Yeah. Thank you very much. Actually, the first speaker has outlined why SAF is necessary, when it is necessary, and so other speakers don't have to repeat that. Uh, we now call for the second speaker, Anil Kumar Sinha from CSIR IIP Dehradun. So over to you. So this is basically, it's a global race, and even in India, it's a 3-horse race. Bharat Petroleum, Indian Institute of Petroleum, and Hindustan Petroleum. And I would say, may the best horse win.
Thank you very much for the kind introduction, and good morning to everyone. And I take this opportunity to thank the organizers for inviting me here. And today I will be talking about the sustainable aviation fuel, same like the earlier speaker, the HEFA technology for making sustainable aviation fuel from non-edible oils. So I will briefly talk about the background, even though it is covered, that right now we are going through the voluntary phase of the ICAO CORSIA, and by 2027, I think it will become mandatory for all of us to have this sustainable aviation fuel as a part of our portfolio to meet the requirement. So looking at the mandatory needs for the sustainable aviation fuel, the Indian government has already set up a indicative target of 1% blending of SAF by year 2027 and 2% blending by the year 2028 for the initially for the international flights. And today, because of the needs of the sustainable aviation fuel, nearly more than 100 airports are distributing SAF. There are more than 34 policies on the SAF, and nearly 46 billion liters of SAF are under offtake guarantees, with 11 approved conversion processes, and more than 5 newer processes are under development. And nearly 42 feedstocks are recognized under ICAO CORSIA. And nearly 211 facilities have been announced across the globe, with the total capacity of more than 70 billion liters of SAF production per year. So among the different newer conversion processes which are under ASTM evaluation, CSIR-IIP own technology for making SAF is the single reactor HEFA process, and it is named as HEFA SKA, and that is under evaluation by ASTM. In addition to that, as we know that there are several newer technologies based on feedstocks ranging from recyclable plastic to methanol to used tires, as well as lignocellulosic feedstocks are under various stages of approval at ASTM. So as we are well aware that the long-term SAF demand is going to increase continuously and is likely to reach more than 600 million barrels by year 2050. So if we compare the different SAF production pathways, the HEFA pathway continues to be the most cost-effective or cheapest among the other pathways like FT or alcohol to jet pathway. Even today, the power to liquid pathway is considered to be most in longer term going to be cheaper. But today, when we consider in the short term, the HEFA pathway remains the cheapest pathway to make SAF compared to the alcohol to jet pathway or the Fischer-Tropsch pathway or power to liquid pathway. So because of that, not only this HEFA pathway is cheaper in terms of the cost of production, but when we look at the default life cycle emission values for the feedstocks using HEFA pathway, so when we see that the overall the gram of CO2 produced per megajoule of the energy for the different feedstocks is lowest for the feedstocks using the HEFA technology, specifically if we look at the used cooking oil. So in case of used cooking oil, the overall the CO2 emissions is only about 13 to 14 gram CO2 per megajoule. In comparison, when we see the 1G ethanol pathway where we use sugarcane as the feedstock, the overall CO2 emissions are nearly 2 to 3 times higher. So if we consider other feedstocks like corn, grain, so in that case, in fact, the overall emissions are even higher than the fossil jet fuel. So because of all those reasons, we believe that the HEFA pathway is not only economical in terms of production cost, but also when we look at the net CO2 emission from the pathway. So we have focused on the HEFA production pathway, and we did some calculation on the different parts of this technology. So we find that overall the capex and opex are less than 20% of the overall cost of the technology, but the feedstock cost is nearly more than 50%, and the hydrogen cost is about 25%. So looking at that, there is a possibility that with time, as we move towards 2050, the cost of hydrogen is going to come down, and there will be reduction in the overall cost of the HEFA pathway for the SAF production. But from the feedstock side, there is a lot of work to be done to reduce the cost of feedstock. If we are able to bring down the cost of feedstock, the HEFA pathway will continue to be the cheapest way of making SAF. So we have looked at the different domestic lipid sources for making the HEFA, and we have understood that used cooking oil will remain as the most economical, considering the overall consumption of used cooking oil being more than about 26 million tons. We are the second largest consumer of used cooking oil after China. And there is a possibility to have at least 2 million tons annually of this feedstock for SAF production. In addition to that, we are also looking at the tree-borne oils, like we have nearly 400 species of identified trees which have the oil-bearing capacity. And along with Forest Research Institute of India, we are working on identifying and also incentivizing these kind of feedstocks from the tree-borne oil, which will augment the overall supply of the feedstock from the tree-borne species. In addition to that, there is an immense potential also in the short rotation crop, as we already see in USA, the camelina is successful, and the overall CO2 emissions, because it is used as a second rotation or third rotation, the CO2 emissions are also lower. So we have been looking at these short rotation crops along with Punjab Agricultural University, and we find that using this carinata as a second or third rotation, it is possible to bring down the cost of the feedstock, add to the income of the farmers. In addition, we are also working on the concept of agri-photovoltaic. So in agri-photovoltaic, it is possible to incorporate the solar energy along with your normal second or third cycle cultivation of the feedstock like carinata. And it will help in increasing the overall energy output from these kind of short rotation crops. So we have done a pilot scale study at a 5-acre land in Kashipur in Uttarakhand, and we have found that it is possible to have about 12 to 5 tons of seed per hectare, and that is additional income to the farmers in addition to their regular plantation that they are doing. So it is grown as a second or third rotation. And I will talk little more on the potential of used cooking oil, like considering the case of the China. Way back in 2010, the Chinese government had banned the use of used cooking oil for cooking. And since then, today China is collecting more than 10 million tons per annum of domestic used cooking oil. And it is the largest consumer of used cooking oil to about 36 million tons. So in India also, we started a similar policy in the year 2018. We are about 8 years behind what China government did. But there is an immense potential which the FSSI itself has identified, that it is possible to have 23 million tons of used cooking oil. And if we do a simple calculation for the net jet fuel consumption in India, which is about 8 million tons per annum, and used cooking oil in India, it is at least 3 million tons. So we will be able to meet at least 20% blending target using used cooking oil itself as the feedstock. So we are using this used cooking oil as a major feedstock. We have been working with several aggregators to augment overall supply of the used cooking oil. So I will just briefly to say that how the demand for used cooking oil initially in China was very low. it was mostly moving to Europe. But again, in Europe, due to some issues about the quality of used cooking oil, probably due to some mislabeling, there was 56% decrease in the import of used cooking oil. And because US started incentivizing used cooking oil, the most of used cooking oil from China started moving to US. But recently, because Chinese government realizing the value of used cooking oil for SAF, China became the first country to have a SAF certified under CORSIA by the international organization. So this kind of model is going to work for India too, that I believe. So I will go into the technology developed by CSIR-IIP. We started the biojet technology concept way back in 2008 at TRL level 1. And at that time, by the year 2010 or 11, we were already producing a SAF by the single-step HEFA technology, which was meeting all ASTM D1655. At that time, the ASTM D7566 was not yet, because it started in 2011. But our technology was mostly done in collaboration with Pratt & Whitney Canada, and we supplied 60 liters of this fuel in around year 2011, and it was shown that its fuels has the potential to become a 100% drop-in kind of fuel, because it has inherently some aromatics in it. And so we continuously developed this technology, and by year 2016, we did the first demonstration test flight in India using this fuel with SpiceJet, and the fuel was found to be very good for the use in aircraft. And then we did some collaborative work along with Indian Air Force, and we did first demonstration in the Indian Air Force aircraft AN-32 on the 26th January 2019. And we got the BIS recognition for the CSIR-IIP SAF in year 2019. And in 2020, we did even the cold condition landing and takeoff in Leh using this aircraft along with Indian Air Force. And we continue to develop this technology. Today we are at the TRL level 7, and the MRPL is setting up a plant using this technology. And we have supplied nearly about 8,700 liters of SAF to Indian Air Force to test on various platforms. And this year, this fuel was also certified on Dornier aircraft and used on 26 January parade during the Republic Day. And right now, actually, we are in the ASTM approval stage. We have cleared the Tier 1, Tier 2 test. And since this fuel is a modification of the original HEFA process, there is no need for Tier 3 or Tier 4 so far. And we are expecting the balloting in the next 3 to 4 months. And right now, this entire technology is being evaluated by all the OEMs. And this is a glimpse of the demonstration we did between Delhi and Dehradun. And it was found that this fuel performed slightly better than your normal jet fuel. All engine parameters were satisfactory. Similarly, in the military aircraft, we did 65 hours of test flight on AN-32 and 25 hours on Dornier aircraft. And just to show, this is a modification of your HEFA SPK, the traditionally that we know the single step process, the two-stage process where deoxygenation is followed by secondary isomerization and cracking. Unlike that technology, we do all these processes: deoxygenation, selective cracking, isomerization, cyclization, and aromatization using a single catalyst. And we produce a mix of SAF and diesel and naphtha. And this is the typical, unlike your two-stage HEFA process, this process produces about 8 to 10% of aromatics, which is a mixture of diaromatics and cycloaromatics. And this makes this process the only HEFA technology which has potential to become 100% drop-in due to presence of these aromatics in the fuel. So in addition to that, we produce nearly about 12% of cycloparaffins. So overall, the hydrogen consumption also in the process is slightly lower because of the formation of cycloparaffins and aromatics in the process. This is the process flow diagram. There is a pre-treatment section. There is a reaction section. It is like a typical hydrocracking section. In the pre-treatment, we have to do the demetallization and remove the all metals before the oil can go into the reactor. And then it goes through the fractionation step. And we look at the indicative yields for the process. We take 100 tons of vegetable oil and 5 tons of hydrogen. We produce 82 to 95 tons of liquid product. Among this liquid product, the SAF yield is up to 70%, meeting all the ASTM specification. There is a paraffinic naphtha ranging from 5 to 20%, and depending on the process condition, it can work in 100% renewable diesel mode, and it can produce 85% of renewable diesel. So briefly, the salient features of CSIR-IIP HEFA technology: it is a single-step process which produces 6 to 8% of aromatics. The process is feedstock flexible. It uses a single reactor to do multiple reactions. It is a non-noble metal-based patented catalyst. We have several patents in US and Europe on that. And the typical SAF yield is up to 70% depending on the type of feedstock. It meets the ASTM D16555 specification and D7566 specification. It is similar to a typical refinery hydrocracking process, and it can be easily used in a refinery. And finally, the current status, we are setting up a 70-ton per day plant along with Mangalore, and EIL is our technology partner in this process. And we have set up a 1 TPD plant for one agrochemical company, UPL India, in Gujarat. And recently, as I mentioned, we have demonstrated this aircraft on various platforms of Indian Air Force. And we produce green diesel. We are going towards the BIS approval. We have done 14,000 kilometers using neat renewable diesel due to its high CTN value. And we are in the final stage of ASTM approval for the process. On the feedstock size, we have been working along with the aggregators and trying to get agreements with the refinery on the used cooking oil, identifying newer feedstocks like poultry fat or animal fat, also working on the short rotation crops like carinata, how they can be useful for this technology. Finally, thank you very much for your kind attention, and I take this time to thanks my colleagues, Dr. R.K. Joshi, Mr. Taslim Khan, Mr. R.K. Baghel, Mr. Parvez Alam, and Shri Salim Faruqi, who are working along with me in this technology. Thank you very much.
Thank you, Dr. Sinha, for highlighting that your robust single-stage catalyst for this HEPA process. Now we would like to invite Akshay Gupta, Honeywell UOP. His topic will be that energy transition with SAP, a path towards sustainable future.
So good afternoon, everyone. Thank you, IEW, for the invitation, and thank you, Mr. Maitra, Mr. Malti. I would like to express my sincere appreciation for this opportunity to meet with you and speak with you today. Ladies and gentlemen, my name is Akshay Gupta. I'm the Senior Manager of Refining and Renewable Fuels at Honeywell UOP. Refiners are facing a new challenge, new world, and a new markets as the drive towards sustainability and lower greenhouse emission accelerates. The end game is to produce low carbon sustainable fuels while maximizing available resources and reducing waste. Today, I'm excited to have the chance to tell you that how Honeywell UOP can help you to speed up the energy transition journey through sustainable aviation fuel. Here is the announcement that there may be some forward-looking statement in my presentation, so please be cautious on how you interpret or use such. Talking about the SAF policy, government mandates and incentives are important to this space. US typically going for the tax credit approach, DOE targeting 3 billion SAF by 2030. European Union is taking a different approach, and they are treating this as a mandate. So either you comply or you pay penalties. UE is targeting 2% SAF in 2025, and they all grows to 70% in 2050. In the rest of the world, there are several other initiatives to produce sustainable aviation fuel. One of them is a CORSIA program, which is essentially an international recommendation that countries commit to reduce international aviation emissions to 50% by 2050. In general, demand for aviation fuel is growing as the aviation sector is difficult to decarbonize. We see the demand for SAF is generally growing rapidly in next few years, as high as 3.5 MBD by 2050. Today, SAF is produced from FOX, which is fat oil grease, is considered a mature technology. However, to meet the growing demand of SAF, new pathways to produce SAF such as eSAF, ETJ, biomass, alder process are needed, and we will discuss those in next slide. Meeting the world's sustainability goals will, of course, require multiple technologies to handle various feedstocks. Here I have summarized the feedstocks that are expected to play the biggest role in the renewable fuels production, and the UOP technology developed so far to process each feedstock. By looking at the UOP portfolio of renewable technology solution, UOP eco-fining technology enables high yields of renewable diesel and SAF through inedible feed sources. With RTP technologies, you can convert biomass such as forest and crop waste to renewable fuels through stabilizing in the alder process, then processing through the eco-fining. Conversion of CO2 and hydrogen into liquid e-fuels through UOP e-fining process that meets CO2 reduction and fuel sustainability targets. And ethanol to jet represents a new revenue stream for ethanol producers to satisfy the needs of the large and growing aviation market. And my colleague Richard Mathers will speak about it in this session just around 30 minutes from here. While new technologies and new infrastructure are developed and designed and built and commercialized, today's needs can be met immediately by leveraging existing assets to create partially renewable feeds from a blend of fossil and biogenic feed. Hydroprocessing and FCC co-processing offers the fastest, lowest path for making renewable fuels. The right pathway varies by the project type based on which feedstock and which assets are available. Honeywell UOP has this history of innovation, drives our technology portfolio for renewable fuels. Eco-fining has been in use since 2013 for renewable diesel and 2016 for SAF production. To further expand SAF production, we have eSAF and E2J technologies in our portfolio. This year, we are celebrating our 50th license of renewable fuels technology, which is eco-fining. And this is the testament of our Honeywell UOP leadership in the renewable fuels technology. In next few slides, we will focus on producing SAF through eco-fining and co-processing. If you look at the eco-fining technology, it produces renewable diesel, SAF, and other renewable products like naphtha, LPG from 100% biofeed sources such as vegetable oils, animal fats, and waste oil. Eco-fining technology is the market-leading solution for producing renewable diesel and jet fuel with several operating plants and more than 30+ years of combined operating experience. Eco-fining technology produces drop-in compatible renewable diesel and a sustainable aviation fuel from a wide range of feedstocks and is flexible to produce in full diesel mode, co-production mode, or full jet mode. There are three ways to produce e-fuels, green fuels through eco-fining and co-processing. First, we can produce renewable fuels through a greenfield standalone eco-fining unit. It gives very good economies of scale and maximum unit flexibility with the target product slate. Second, through revamping of existing hydrotreating and at moderate capital expenses, it is faster time to production and provides limited feed flexibility and economies of scale. Third, through co-processing biogenic feed, it is faster implementation and it produces blended fuel with minimum capital investment. So in our eco-fining process, we have a couple of ways where we offer this as a single stage or two stage. Single stage eco-fining technology offers a fast and cost-efficient path into renewable fuels with moderate product flexibility. On the other hand, two-stage eco-fining provides maximum feedstock and product flexibility. If you look at the process, right-hand side, feedstock is pumped to process pressure, mixed with recycled hydrogen and sent to hydrodeoxygenation reactor, where the renewable oil is saturated and completely deoxygenated with high selectivity towards renewable fuel boiling range paraffins. The effluent from the deoxygenation reactor is separated to remove carbon dioxide, water, and low molecular weight hydrocarbons. The resultant product is mixed with additional hydrogen and then routed to hydroisomerization reactor, where a branch chain paraffin product fuel is produced. In this manner, the cold flow properties or the freeze point of product are adjusted to meet the required seasonal specification. Isomerized product is further separated from excess hydrogen in a conventional gas-liquid separator. The liquid product is sent to the product recovery and to further process and through the conventional distillation steps. These are the various operating plants producing renewable fuels across the regions. As you can see, feed capacity varies as low as 3,000 BPSD to 35,000 BPSD. Diamond Green Diesel, which is our first eco-fining project, operating unit of producing green diesel, while World Energy Altair is our first eco-fining operating unit producing SAF. In the next few slides, we will focus on hydroprocessing and co-processing. In a typical hydroprocessing flow scheme, feed is processed in the reactor section to convert into valuable products. These products are then separated in the frac section. Typical configuration, UOP union feeding like hydrotreater, kerosene hydrotreater, VGO hydrotreater, coker hydrotreater, remove most contaminants and improve product properties like C10 number or cloud point. For the unique cracking section, depending on the feed severity, customer processing objectives like desired product yields, product properties, existing constraints, the configuration can vary from one store to single stage to two-stage recycle unit. So let us look at the co-processing. Including biofuel feed into the existing asset is a key enabler to quickly meeting sustainability targets. It is a commercially proven technology and decrease overall CO2 reduction while factoring into scope 3 emissions. UOP has proven experience and can provide a phased investment approach solution to our customer. Phase 1, if we talk about 3 to 5% biofeed with no minor revamp and can be implemented with the catalyst reload. Phase 2, as we increase the percentage of biofuel up to 12%, it needs to be evaluated and revamped for hydrogen requirement, hydrogen purity, recycle gas requirement, and to meet the desired catalyst life. This is a minor or mid revamp. For biofuels greater than 20% in blend, unit needs to be evaluated and revamped for metallurgy, upgrade additional new equipment to meet hydrogen cycle life and product property. For a 50,000 BPSD VGO hydrocracker unit co-processing 5% of renewable, there is a net CO2 reduction of 170,000 metric tons CO2 per year relative to a fossil fuel feedstock. So these are the various feedstock that can be processed. Biofeeds, of course, introduce catalyst, poisons, and contaminants at high levels than fossil fuel. The most important properties of the feed is the free fatty acid, FFA, content, metals, chloride, phosphorus, olefin content, nitrogen level. Typically, biofeed requires pre-treatment, water or degumming or bleaching. Untreated biofeed is, of course, not recommended as gums may lead to fouling and plugging in the feed section. You can also see variation in hydrogen consumption between a highly saturated feed such as tallow and a highly unsaturated feed such as soybean or camelin oil. Let us review the hydroprocessing versus co-processing chemistry. Hydrotreaters and hydrocrackers are designed for reduction of sulfur and nitrogen. Hydrogen displaces a sulfur or nitrogen atoms into an organic molecule. This chemical reaction is difficult and requires very active catalyst. Hydrotreatment of vegetable oils means splitting a triglyceride into the paraffins. Deoxygenated triglyceride have chemical structures similar to diesel and jet, but less branched, right? So this chemical reaction is very reactive and requires low active catalyst. Looking at the feed composition of biofeed, biofeed, of course, introduce catalyst, poison, and contaminants at higher than fossil fuel and requires pre-treatment, which we talked about, water or acid degumming or bleaching. Untreated, of course, not required. Feed has lower sulfur, higher C10, but also considerably higher cloud point than the fossil fuel. Looking at the hydrogen demand, biofuels have significant higher chemical hydrogen demand than fossil fuel, drive distillates. Biofeed processing generates CO and CO2, which can accumulate in the teat gas and lower the hydrogen purity. In terms of metallurgy, chlorides and free fatty acid in biofuels as well as CO2 generation during the processing requires metallurgical review and may guide the selection of the feedstock or amount of biofeed that you want to process through co-processing. So let us look at various co-processing revamp scenarios that we discussed earlier. With minimum or no modification, you can process less than 5% of biofeed. With minor modification, you can process 5 to 10% of biofeed with compressor or modification and possibly some metallurgy upgrades. With major modification, you can process typically 10 to 20% of biofeed, but that needs equipments in the reactor section and the metallurgy upgrades. Summary and takeaways. Of course, the dramatic growth in the demand for renewable and fuels technology illustrates that fuel producers are accelerating the adoption of solutions to help meet mandates and decarbonization goals. Technologies such as eco-fining, eSAF, ETJ, biomass based on new feedstock are essential to meet growing SAF demand. Early engagement and leveraging existing assets quickly and economically are key for a sustainable future for SAF. This is the last slide of my presentation. Please do visit our Global Biofuel Alliance exhibition in Hall 1, where we have showcased our renewable technology offering portfolio. Ladies and gentlemen, thank you very much for your time and attention. Appreciate it.
Thank you, Sri Akshay Gupta, for highlighting that customer to navigate the spectrum of options for SAF productions through eco-fining, ethanol to jet, and e-fining. Next, our speaker, we would like to invite Dr. Narasimharao Kanna, Manager, HPCL.
I thank IEW for selecting our abstract for the oral presentation. Today, I would like to introduce our technology, HP Trijet, predominantly the technology for conversion of UCO to the SAF and green diesel. So basically, we are talking about triglycerides conversion to jet fuel. So that's why we call it the name as Trijet. So if we see the global carbon dioxide emissions from aviation industry is concerned, so it's around 2% around in 1990, and it is will be around 2. Yeah, it is about to touch around 3% at 2020. So there is substantial improvement in terms of CO2 emissions from the aviation industry is concerned. So if we see the region-wise, the emissions of CO2, so compared to any other region like North America, Asia Pacific, China, Europe, Middle East or Africa, Latin America, the many folds of CO2 emissions from India will be almost six folds compared to other regions. So there is a lot of scope for India to work on to reduce emissions from the aviation. Right. So to reduce the CO2 emissions from the aviation, so the CORSIA, and we have seen from the previous speakers the importance of SAF, and although there are technology advancements on operational improvements and aircraft technology is also expected, but the majority portion of the reduction comes from the SAF. So we can see there are different feedstocks like 1G, 2G, 3G feedstocks, like a waste from agricultural residues, municipal solid waste, and used cooking oil and tallow animal oil. So and also like a different edible oils like vegetable oils like corn oil, soybean oil, and rapeseed oil and palm oil, and also 1G feedstocks also we can see there. So why we are interested about HEFA route? Because of the high distillate yield for production compared to any other technology we see. So HEFA route is giving around 0.3% of the distillate yield compared to the ethanol to jet and GFT of municipal solid waste and GST of any other route is concerned. So recently the government of India has given the mandates of the SAF blending in the ATF, so which will be projected to be 1% by 2027 and 2% by 2028 and 5% by 2030. And we can see much more advances from the Europe is concerned, so where they are targeting 2 to 5% by 2025 itself, and which is going to touch around 50% by 2040. So let's talk about our technology, which is HP Trijet, where we convert used cooking oil or per se any vegetable oil is concerned to SAF or naphtha, propane and aviation fuel. So the novelty lies in the majority, mostly in two parts. One is the pre-treatment of the feed and other is the catalyst. Excuse me. So the reactions, dominant reactions in this technology is concerned. So when we talk about the triglyceride backbone, we can see the backbone of triglyceride there. So where we have to remove the oxygenation by three routes. One is hydrodeoxygenation, decarboxylation, and decarbylation. So where you selectively form a green diesel. Further, we have to crack the green diesel towards sustainable aviation fuel and green naphtha, and then remains the unconverted renewable diesel. So to perform this like a cascade reactions from triglyceride to the SAF, so we have developed an indigenous catalyst, so which can perform this in a single step, similar to IIP what they have done. So when we talk about UCO pre-treatment, which we have a novelty in this, so where we have also seen from the earlier speakers the importance of acid degumming and bleaching for removing impurities. So during our analysis, what we have identified is that apart from these impurities, there also lies some impurity of organic chloride. So this organic chloride predominantly arises when from the household cooking of adding a table, the common salt or table salt. So where the chloride reacts with the free fatty acids and forms some organic chloride. And this organic chloride tend to form HCl during the reaction, and that can cause some corrosion issues to the reactor. So to mitigate that, we have developed in-housely a process where we can remove selectively organic dechlorination without any impact on the feedstock yield. So if I see the overall, the main properties of the UCO before pretreatment, after pretreatment, we can see the presence of metals like sodium, iron, phosphorus were came down to less than 1 to 2 ppm. And inorganic chloride, of course, it can come to 1 ppm. And the important thing which we want to highlight is organic chloride, which is a 15 ppm, so which has came down to less than 1 ppm. And further, the other impurities like alkali earth metals like calcium, magnesium, and potassium also came down. So the catalyst what we have developed indigenously was basically tested in high throughput automated reactors, followed by the semi-pilot, followed by the pilot scale. And that catalyst should have a following functionality to get the SAF. So the functionality lies in, as I mentioned, the deoxygenation. The deoxygenation can be happened via removal of water molecule or by removal of carbon, where we remove by carbon dioxide or carbon monoxide. So it is, if we are targeting lower hydrogen consumption, then we have to target by decarboxylation and decarbonation. If we are aiming higher yield of the SAF, we have to target on removal of oxygen by water route. So we have a catalyst functionality on deoxygenation is concerned, and we have functionality on selective cracking of diesel to mostly to the ATF. And we have also isomerization function in the catalyst, which will isomerize the ATF molecule to meet the freezing point spec of the ATF. And we have also some the binders which to keep the physical strength because of the high pressure reaction and the high temperature reaction is concerned. And what are the key differentiators? The key differentiator lies in the feed agnostic. So we have done a multiple or a plethora studies on different feeds. Of course, your SAF yield varies on, depending on the carbon length of the vegetable oil, your SAF yield will be changing. But the catalyst can be we have done a lot of vegetable oil based studies to see the effect of the catalyst stability and the yield is concerned. And we have a tandem functionality, as I mentioned, the deoxygenation, cracking, and isomerization. And we can also selectively produce either green diesel or ATF, like IIP, what they have also shown. So these are the overall mass balances. So we take about used cooking oil. So when you send around 96% of UCO with 4% of hydrogen, we end up with 40% of aviation fuel, and we end up with 31% of renewable diesel, 10% of green naphtha, and a gas of 16%, which including the propane, H2S, and C1, C2. So we're also working on to improve SAF yield by recycling the renewable diesel to higher than the 60 to 70%. So the properties we have thoroughly checked from the semi-pilot, from the semi-pilot to the pilot scale. So where we have done the catalyst life cycle estimations, and so I would like to highlight on of course all the properties are also matching the required jet A1 spec, but I would like to highlight on the freezing point spec what we are getting there. So where the spec is around -47 max, and we are able to achieve -75 consistently with different kinds of vegetable oils. So we know that the importance of freezing point of the aviation fuel. So we are able to selectively get that in a single step with the single catalyst is concerned. And also we have measured the green diesel specs with the EN 15940, and we are able to achieve the higher cetane number and all we have. So we have also the issue of lubricity, but one can dose lubricity improver for getting the certain lubricity. So what are the key challenges we are presently facing in this technology? So we foresee that feedstock availability, where the policies should be strengthened to get the feedstock availability should not be a problem when the plant is running. So that's why we are working on different plethora of feedstocks, either it be non-edible or edible sources of plant, and the availability of UCO is a concern. So where we need to be having some MOUs with the companies which can supply us this UCO. So the high exothermicity is one of the main problem in this reaction. So where the first reaction is concerned hydrodeoxygenation. As soon as the catalyst sees the oxygen, when remove the water molecule, so we see very high exothermicity in this reaction. So where we have to focus on the blending of the diesel feedstock again in the feedstock, or we have to focus on quenching with hydrogen. So product yield, so selectively achieving the high desired product yield and minimizing the green diesel, which is not a particular mandate in India. So that is the one main challenge in this technology. And if you see the typical catalyst stability, so we are working on one step, so where the catalyst stability is not typically a hydroprocessing like 3 to 4 years. So the catalyst stability is lower in this aspect because of the production of high amount of water in the reaction, and that can leach the catalyst sulfur. So the catalyst sulfur is prone to react with this water molecule and tend to leach it. So this is one point of concern and a lot of scope to work on this kind. And we have seen the hydrogen consumption previously, it's almost 4%, which is very much higher compared to typical hydroprocessing reactions. And if you're targeting to use a green hydrogen for this, and again the cost of the overall cost of the product will be increased. So we need to emphasize on the achieving lowering the hydrogen consumption, either targeting decarbonization, which has a higher profitability. So one more issue here we identify the challenge is feed contaminants. We have seen a lot of heterogeneity in the feed contaminants from different parts of India. We have collected the feeds from all parts of India like north, east, west and south. So we can see the lot of heterogeneity in the contaminants, and the rigorous treatment is required, like organic chloride as I mentioned, which is one of the predominant impurity for the reaction operation and all. So that should be addressed and so forth. So overall, to summarize, so we had developed a single-step catalyst which can produce the SAF around 40%, and it has this in-house catalyst. Presently, we have scaled up this catalyst to 140 kg, and we are further scaling up to 1 ton scale. And this catalyst can selectively produce either SAF or green diesel with the same catalyst under respect to reaction conditions. And the catalyst was successfully demonstrated at the lab scale and pilot scale. And we are going ahead with a 7.4 KTPA capacity of this plant at the HPCL Visakhapatnam refinery. And this plant will be commissioned by 2026 December. And we're also planning to have one more plant at Bahadurabad with almost 3 times capacity of 20 KTPA. So, presently we are we have producing the SAF at a pilot scale. We have almost collected more than 500 liters. So we will be going for certification and approvals for that. That's all. Thank you so much. And I request you kindly visit our HPCL stall at Hall 2. Thank you so much.
Thank you, Dr. Khanna, for presenting that trijet chemistry route in that SAP productions. Now, next we would like to invite Hemant Paradkar, ExxonMobil. He will be presenting that maximizing yields of renewable diesel and SAP with ExxonMobil process technology.
Good afternoon, everyone. It's a great privilege to be here today. I'm going to talk about, maximizing yields of renewable diesel and SAF. So I'm from ExxonMobil. For next about 14 minutes, I'm going to talk about it. So let me start with the organizational setup. Just about 2 years ago, we structured our business units. We had more than a dozen, I would say, 5 years ago. Now we are down to 3 business units. One on the right side is the LCS, which is the low carbon solution. And that's something which is just 2-year-old baby. The focus there is all about hydrogen. The focus is on the LEF, low emission fuels, and CCS. So that's the newest business unit. The rest 2 are, converge into that. The leftmost is the one we call upstream, and the middle one is product solutions. So fuels, the lubricants, the all the chemicals, solid and liquids are all there. And all the support organizations like technology, manufacturing, and all are below, as you can see. So having enabled ourselves, we have to offer you, and this is what I'm going to do. I'm going to talk in 2 parts. The first part is going to be renewable diesel fuel technologies, basically isomerization, dewaxing, all about that, and how we can integrate that and offer you the whole package. The second one is about e-fuels, or you can talk methanol to jet. So I'm going to proceed on the first part now, which is basically renewable diesel distillate fuel technologies. Now this graph, I'm going to develop on it. This is truly a pride and a really one which I would like to highlight. It was in 1990s when Heritage Mobile came out with MIDW catalyst. This isomerization dewaxing catalyst in 1990s changed the world, the way fuel delta cloud was being managed. Subsequent to that, we came out for lubricants, and again, it had a great impact overall. Now, with all that knowledge and legacy and pride, we are coming out for the bio. So it's a bio isomerization dewaxing catalyst. Acronym is BIDW. Now let me dwell upon a little bit what that isomerization dewaxing catalyst says. On the horizontal axis, it's a delta cloud. So more on the right, the higher the number. As we know, typical feed which requires isomerization and dewaxing is N-paraffins. The N-paraffins are typically C16 or C18, and it could be from anything, a tall oil to soybean oil, the tough to easier oils. Usually what we end up doing is single branch isomerization, and that solves only problem partially, what we can do without impacting the yields is making it multi-branch, and that gives yields much higher than many others in the marketplace today. So hold back and see. You have been hearing a lot today and earlier out that there are so many feedstocks available. The crucial thing is how to get yields and how to get product suitable for the application. And I believe we offer that very well. Let me move to the next slide. Now this is a schematic diagram on the top right. I'll take you to the right bottom graph. Look at the axis over there. It's 2,500 days. And this is a true plant which is working in Scandinavian countries for such a long time, and the data is from that. Now if you see the light blue color, what I would like to highlight, and please have a look at it, it says about 25% blend of the feed, which is a bio feed, and it goes all the way up to 100%. Now, it's not a one single feed, but it's a changing feed. So you can see how catalysts demonstrate the stable operation in the varying feedstocks. Now, on the bottom side, the dark blue shows that at all these variables, the feed rate remains constant, and this is truly commendable. In a similar axis, horizontal being 2,500 days, the point I'm trying to make over here is you can truly change your feed and your delta cloud point depending on the applications you want to make. For example, you may like to make a Euro 5 compliant, or one fine day you would like to make it Nordic compliant. And that being the case, our catalyst has all the capability to adapt to it and meet your requirement. This is one more slide on a similar axis, 2,500 days on a horizontal axis. This is about cycle length and maximizing the diesel yield. So if you see the light blue color dots, it's 99% all through the day, all through the last days. And if you see the WABT, which is basically weighted average bed temperature, it remains stable. Now this stability is very important given the fact that there were multiple power outages, feed N could have been challenges fewer times, and the catalyst grade which was used was BRDW3 over there. So this is a graph which I would like to highlight, and I would move to the next page. Now I'm going to dwell upon this for a couple of minutes. This slide on the left hand side is a summary. The summary says that this catalyst, as delta cloud increases, it becomes even more competitive. And that is very well summarized in the numbers in the right hand side. Now this is a true data that we have, but we can't share the whole data with you, so we have made a somehow equivalent numbers out of that. And if you see the one which is highlighted, that is for the two vertical axes, which says that 30 degrees C delta cloud point and 60 degrees C delta cloud point. And comparing to the options available in the market today, as we go more on delta cloud 60 degrees, for a similar percentage on a weight basis, the yield is 6 to 8% depending on the feed and other operating conditions. And if we take a plant size of 10 kbpd, that's even more pronounced on a weight. I would say it is about 570 to about 800 barrels per day. If you talk about translating that into dollars per year, that's significant. At 60 degrees delta point, it would be as good as $50 million, $40 to $50 million. The point over here is that our catalyst has a high selectivity, it offers a great dewaxing, and it is a long cycle length. This is a real thing. ExxonMobil is putting money what we preach. So we have Strathcona refinery coming up. It's more than $500 million committed over there. This is about 20 kbpd. Here, interesting part is the feed is expectedly couple of different bio feedstocks. oils, you can say. And hydrogen is green, which is from the green electrons. The CO2 is captured and sequestered. So it's going to be a really unique project in many ways. So it's coming up. And again, this catalyst uses our isomerization dewaxing catalyst, which I've been talking for the last few minutes. This slide is overall what we are offering. I spoke a lot about isomerization dewaxing catalyst, but this slide says that, okay, we have a HDO reactor which gets the feed, and we can design from left to right depending on what you want to optimize. You want to optimize jet, you want to optimize diesel, what is your feed, and that is summarized well in the page which comes now. So we have 3 catalyst suites to offer today. The 1 and 3 are the extreme ends. You can make 1 is all about diesel, 3 is all about the jet, and in between is all about, you know, which you want to both. So now this high is truly high. I can't quantify the number on this platform, but we can talk about it. But we have this range to offer, and this is all about, you know, all the, you can take UCOs, fat, all the vegetable oils, and a couple of other options there as a processing, as a feedstock. So that's about from my side for the bio side. Now I will switch to the next part, which is synthetic fuels. And so now in synthetic fuels, we have a huge legacy of methanol to jet. The one on the left, which is a fixed bed plant, is more than 40 years old. It's in New Zealand. As you can see, there are 5 reactors, which is to a certain extent quite a challenge, I could put it that way, because one reactor is always under regeneration and other 4 on different stages of what I call regeneration. So the temperature profiles are different. Unique about this is the gas is recycled to you know, as a coolant. So there's a large compressor, a lot of energy inefficiency. While as against that, the one that we offer in fluidized bed is far efficient, very simple. It has a catalyst which continuously is fed there. The catalyst takes over the heat. It is generated into steam. It's very efficient, and the summary is on this table. So if you see over here, we have 2 technologies, but we believe that fixed bed is more expensive versus fluidized bed, and the reasons are so. One is the single reactor, heat integration, obviously the less piping and all over there, pretty steady, catalyst activity rate, and of course among that there is no switching of reactors. So do we have a plant operating? Yes, we do have a plant operating. It's in Chile. This is for one of the leading motor car race manufacturer. I can't tell the name because we don't have authority to do it, but this is based on a green electrons from the windmill as shown over there. So there's a green which is converted to hydrogen, and the CO2 which comes there is from a brewery. So CO2 is also very, very green. It's get converted into the gasoline. That gasoline is of course used for race cars. So that's what it is. And this is the news. NEOM, one of the prestigious project in Saudi Arabia, they are gone for it. This is all in public domain. They're putting up a plant over there, and we can talk about it sideways if you want to know more about it. Now let me go to the most talked about today, which is SAF. We have methanol to sustainable aviation fuel, which is available. This technology has been around for a long time. It's just that it is gathering more interest these days. One of the caveat over here is we don't license it the way we do all other technologies. What we do over here is we actually would like to have something more than that as we talk to the whosoever would intend to use it. This is a very simplified diagram over here. The step 1 is convert that into olefins. Step 2 is of course oligomerize it, and step 2 and 3 is basically hydrogenation and fractionation to get the isoparaffinic kerosene stream that we want. So this is a very simplified diagram, and we believe this is we have an edge in many ways, because first of all, this is tunable to what you want. You can in fact make a diesel if you wish to, but this is more being proposed for jet. Methanol, it can be fungible, it can be gray, brown, green, whatever you want. This is not like a Fisher Tropsch where you are worried about gas coming to you and handling it. So feedstock management becomes easy, and there's a flexibility because there is an O part to it. Methanol to olefins, somebody wants to take that O to olefins and their future derivatives over there. That's also possible. I'll talk about ASTM process now for a couple of minutes. We already initiated it. So we already started it. We made some 200 gallons of that. We're in a very advanced stages of qualification. A couple of my colleagues are leading the whole ASTM process. And obviously, it requires some blending. So it will have a blending with the crude oil-based aviation fuel, and it goes into there for the usage. So to conclude over here, we have this excellent isomerization dewaxing catalyst, which helps for biofuels. And on the other side, we have this methanol to fuel. We offer gasoline and jet. And we already undertaken all the qualification processes required for methanol to jet and methanol to other things. So I'll stop here. That's all from my side.
Thank you, Hemant Paradkar, for highlighting that isomerization catalyst for biofuels as well as synthetic fuels, and that SAF also, methanol to gasoline. Now that our last speaker, we would like to invite Richard Mathers, Senior Director, Sustainable Technology Solutions, Honeywell UOP.
Thank you. So if we step forward, the first thing I have to recognize is we started off talking about SAF and the marketplace, and I will just maybe close off with a similar message on that side as well, as we look towards the actual marketplace for sustainable aviation fuel, but maybe also looking at it from a different perspective with respect to another alternate feedstock. So as I say, to start off, colleagues and former presenters have already shared some market trend data on this, but I'll re-summarize. Because for decades, governments across the world have framed policies that incentivize or mandate the use and production of renewable liquid fuels with lower life cycle emissions versus fossil fuels. This is a visual representation of the policy activity around the world related to renewable fuels. Policy is critical to this effort and to the market. The fact of the matter today is that the renewable feedstock is more difficult and more costly to process than crude oil. So the right policies are actually key in driving the infrastructure growth. With 114 countries participating in CORSIA, the past 10 years have seen a significant increase in the amount of renewable fuels specific legislation. Much of this legislation is aimed at incentivizing the use of the renewable fuels, but there's also a lot of public funding that's available to foster the technology and the project development. Based on the policies today, there's a real and growing market for renewable fuels and especially sustainable aviation fuel. And that trend is only expected to grow. I appreciate this is a repeat of my colleague's slide earlier on, but maybe gives people a chance just to refresh on this. Aviation is the hardest sector to decarbonize. The greenhouse gas emissions from the global aviation industry account for just under 2% of global emissions. So displacing aviation fuel poses a unique challenge when compared to gasoline or to renewable diesel. Aviation requires an energy-dense fuel, and it needs to be in proven and reliable engines. So when it comes to decarbonizing flight, reducing the carbon intensity of the actual jet fuel is the most practical approach. To that end, global aviation industry has developed a positive target which proposes net zero emissions by 2050. The US Sustainable Aviation Fuel Grant Challenge, they target 100% of aviation fuel to be SAF by 2050. The EU's Refuel EU regulations, they're targeting increased SAF percentage up to 70% in 2050. Like a lot of the presenters here, I want to demonstrate credibility. Honeywell UOP launched its eco-fining technology over 15 years ago. The process was focused on the use of HEFA feedstocks for the production of renewable liquid fuels, predominantly renewable diesel and renewable sustainable aviation fuel. I think I skipped on one there. The first unit started up in 2016. And the first revamp started up a year later in Italy. And then the first unit to produce sustainable aviation fuel started up in 2016. I seem to be in an auto here, but if you look in the top right-hand corner, very quickly, the top right-hand corner of the slide noted a multitude of companies. Those are the companies who, in 2023 alone, chose Honeywell UOP to be their technology provider for the production of renewable fuels. As many of you know, the market price of cooking oils is climbing, and the availability of SAF production is already limited. So, moving forward, their targets discussed earlier, alternate feedstocks that upgrade are absolutely essential. Here I've summarized the feedstocks that are expected to play the biggest role in SAF production and the UOP technologies developed to process each of these feedstocks. Each of the feedstocks have their benefits and their drawbacks. Vegetable oil. Vegetable oil, easiest to process, but it's also the most limited in terms of supply. Biomass. Biomass can be difficult to consolidate, and the pie oil from biomass itself poses challenges whenever you attempt to process it in large quantities. Carbon dioxide, CO2, which is obviously the biggest thermodynamic challenge on the list, but at the same time, the CO2 pathway has actually got the highest cost of production on the list, but as a feedstock, it's hugely abundant and inherently circular. Ethanol is a really promising solution, and it's gaining rapid interest, especially actually in the Americas. However, European legislation restrict the feedstocks that are considered to compete with food supply. So we know that India has a high focus on ethanol as a blended fuel, albeit we have seen the recent issues regarding the challenges on the availability of 1G ethanol. So this is where the second and third generation ethanol will have a play. So I've deliberately highlighted the ethanol route, and I'll step into that in a little bit more detail. So if I step now into a bit more detailed focus on Honeywell's approach to ethanol conversion to jet fuel, it's a relatively straightforward approach. You have the dehydration of ethanol to produce ethylene. That's followed by oligomerization of the ethylene to heavy olefins, and then finally, the hydrogenation of the heavy olefins to jet fuel. So while I've mentioned ethanol for the production of SAF, the Honeywell ethanol to jet technology enables the production of a wider range of renewable liquid fuels. That said, the vast majority of the interest in this technology is on maximizing the SAF production, with any naphtha and renewable diesel being considered more as side products, albeit these side products that could be further back integrated into the process to lower the carbon intensity. My apologies, I seem to have a problem on the ones jumping forward. If I speak about step one, so step one is ethanol dehydration, where the ethanol is dehydrated to ethylene and water. This is where we started using the over 100 years of our process technology experience, as well as our 50+ years of catalyst development experience. Again, I'll switch back to number one. So through our methanol to olefins technology, which is already commercialized, we have experience of processing the olefins in the presence of oxygenates and addressing the challenges that we see around fouling and contamination. There are already 7 commercially operating MTO units, all at significant scale. We also have many years of experience of designing reactors for endothermic processes, such as our propane dehydrogenation process. If I move now to steps 2 and 3, this is where we convert the olefins to jet. So the light olefins are first routed to a oligomerization section. This is another space that UOP can draw on its deep well of experience. Our oligomerization technologies date back to the 1950s with the CAT poly process, which converts C3 and C4 olefins into gasoline blend stock in hundreds of units around the world. Since then, we have developed a number of other designs for oligomerization of heavier olefins, including INALC, commercialized in 2001, and Cataline, commercialized in 2016. We have modified the existing designs and the catalysts, and based both on pilot plant testing and operational experience, we have designed an oligomerization section that is highly selective to jet through fractionation and recycle up to the target length. Similarly, whenever it comes to the hydrogenation step, we have got decades of experience in the selective hydrogenation through our SHP and CSP processes. We have leveraged that experience to design the olefin hydrogenation section downstream of that oligomerization. That was a very swift walk through Honeywell UOP's ethanol to jet offering, as well as a nod towards the other renewable fuel liquid technologies that we have in our portfolio. Although the ethanol to jet technology was only launched in late 2022, we have already seen significant interest globally. Already, several companies have decided to use Honeywell UOP ETJ for their sustainable aviation fuel production. Shown here are 2 of the announced projects, one with Summit, the other with Grand Bio. There are also additional ongoing projects. Unfortunately, those are confidential, so we can't mention them by name. But in short, Honeywell UOP is the market leader in SAF production process technology, and we're ready to support India. We've heard a lot about the indigenous and the focus on India for India as well. Now, for more than 80 years, UOP has been the respected technology leader in India and a long-standing partner for many of the local refining and petrochemical industries. And from a local perspective, UOP India was heavily involved in our ethanol-to-jet technology development, so much so that the UOP India was awarded the Golden Peacock Award for the Innovative Product Award at the 30th Annual World Congress. That was for the revolutionary ethanol-to-jet technology. I was going to finalize in this infographic, but trust the short presentation has provided some interesting information on the use of ethanol as a feedstock for the production of sustainable aviation fuel and the ability to make major steps forward towards the decarbonization of the aviation industry. Thank you.
Thank you, Richard Matthews, for presenting that ethanol to or olefin to jet fuels. So, we have heard 6 presentations, very nice presentations, all leading to that SAF productions, various routes, and various challenges they are addressing. Some are at different stages of development. Some are claimed to be developed. It has a lot of challenges, including that various steps involved in these conversions. And all that presentations, they are trying to cover all the challenges like various steps of chemistry, particularly the chemistry base, that HPCL, BPCL, and our IIP, CSIR-IIP. They have covered, covered that challenges and the steps they are being taken care. And also the developed technology from EOP, ExxonMobil. So all are aligned to reach that goals, stepwise goals, starting from that 2027. So thank you all the presenters for very good presentations, nice informations. So due to shortage of time, I think we may not be going for that questions answer sessions. They can directly interact each other during that interaction shares or in online. They can interact. So you would like to take?
Yeah, you heard a lot about SAF. So let me summarize. It's a 3-horse race in India. And right now, IIP is slightly ahead. And their claim to fame is a single-step SAF technology. But Hindustan Petroleum is going strong, and they have identified pre-treatment as a very important component for SAF technology, and they are going ahead with the demo. So anyway, I think between the three, we wish you all the luck. Now, for the HEFA technology, I think UOP with 50 licenses is clearly the global winner. And in the case of methanol or alcohol to jet, I would say that right now is not the time because it is very expensive. But you have 2 technologies, either ExxonMobil or UOP, and both are great. Again, you may still choose an Indian technology and then put a global catalyst. But what I'm saying is, it's an interesting time, and within the next 1 or 2 years, all refiners have to decide on SAF. Thank you.
Okay, thank you. We will close the session. Thank you to all of you.